Hi, everyone. I'm Blake Bourne from the National Renewable Energy Laboratory, introducing of InDEEP. Really looking forward to talking to you all. I'll turn it over to Joachim.
Hi, everybody. Hello. My camera just this second decided to take a quick break. I hope I'll get that sorted so you can see who I am later on. Yeah, I just want to quickly say that we're running a second series of webinars. We'll cover the same themes in the same sequence as previously, and we'll go into a bit more depth. And that's what we're doing here today with a general introduction into wave energy. And I will hand it over to Ryan for a second.
Yeah, just a few logistics for everyone. First, please note that everyone is joined in listen-only mode. This means your microphones will be muted and cameras turned off during the presentation, just so that we can get through all the information. If you do have any audio issues, we recommend trying to connect over the phone. You can reach out to me if you need assistance doing that. If that doesn't work, you can visit the Zoom Help Center, or you can message me directly. I'm happy to talk you through any issues you may have. We also are going to be presenting quite a bit of information today, but we very much want your feedback, your comments and questions. So please put those questions and comments in the chat box, and we will be monitoring that throughout the presentation, and we will go through those at the end of the presentation. And also, one final note, this is being recorded and it will be posted afterwards for reference in future use. And that's all for me. Back to you, Joachim.
Great, Ryan. Thank you very much. So what we want to do today is we want to reflect a little bit on the previous webinar, because I believe some people haven't watched it. It's also a while ago. And since these things build onto each other, I've put agenda together on the right-hand side for the day. And previously on the left-hand side, you see the previous agenda. I've also incorporated with white headings the previous slides. We'll go to them really fast. I just want to use them as visual reminders of what was discussed the last time without going to the content, and then build on these to different degrees in the different sections. So the agenda has only changed a little bit, that following from technology, we'll have technology development methods and a bit about history. Okay. And a little bit more on the prize itself. Blake?
Sure. Thank you, Joachim. So the prize is a $2.3 million pool of money. There's three phases, as Joachim essentially illuminated. The incentive of the prize is we want early stage researchers and a solver community to help address these technical challenges that are associated with wave energy underneath the banner of distributed embedded energy converter technologies. I'll turn it back to you, Joachim. Thanks.
Just a little more here.
Sure, I can speak to this. So if there's questions about the prize overall, we have recorded all of our conversations. And also the participation in the webinar contributes to your score on the leaderboard. We know that it's important for you to complete the leaderboard eligibility form. And then also please visit the website at www.herox.com/InDEEP for additional information. Thanks, Joachim.
Great, Blake. Thank you. Okay, so we started with ocean waves. Last time we went through simple geometric description of waves, understanding that they have different periods and lengths, and that they deform when they interact with other things like shoreline. We've looked at the spectrum of different waves that there are, from tidal waves to capillary waves, and we understand that the most energy content is in the ordinary gravity waves that we are chasing here. We looked at the particle motion, and with some animation, understanding the rotation plus shift of a typical wave here, and then a different wave shape was also displayed here. Clearly, in the real sea, things are much more three-dimensional and non-uniform. So that's a visualization of that, and here real sea on the right-hand side. So that's what we talked about last time with waves, and this time we extend this to the wave-body interaction. So what I want to do here, and please forgive me for showing you one equation, I want to talk about the main forces that a floating body experiences. A floating body is simply described as a geometry freely floating in the free surface with coordinate system and everything described. We can also briefly consider multiple bodies and how they notice each other. So this is the equation I'm referring to. So you see that's ordinary differential equation, 1 degree of freedom. The most simple form, we can talk about body forces of floating bodies and body motion later on. So you see inertia terms, you see damping terms, you see restoring terms, and you see external forces that drive and interact with the motion that comes out of this dynamic system. And we look at some of these terms in more detail. For particular interest are things like added mass and radiation damping. Okay, so as mentioned, this is, as you've all seen to exhaustion, single degree freedom mass spring damper system, or it can be simplified to that. Okay, let's look at the restoring force, hydrostatics. So if we have a body that's in the free surface, it has a restoring force that is a function of the displacement. In heave, clearly it's a function of the water plane area and the volume and the change in buoyancy. In pitch, it's dependent on more aspects. It's also with the center of gravity and center of buoyancy. In surge, when we move it so that it's horizontal, we don't get a different displacement, a different buoyancy, so we don't have a reaction. It's neutral. And just in terms of stability, pitch, of course, can be unstable if the arrangement is not as desired. So capsizing is possible. It can be very stiff, very soft. And in heave, when you think of large displacements, like in pitch, it's possible that there is a local stable area, and if you go to a certain amplitude, it might become unstable. Let's go to the next one. Oh yeah, first of all, I wanted to go back to the equation and show which term we're talking about here. So this is the displacement, and the displacement term restoring force, excitation force. So let's think of a body in waves. There's two sketches here. What we'd like to distinguish is the orientation of the surfaces that experiences wave pressure. So for example, on the top right, you see the red line, which is pressure that will be relevant for heave motion. The blue one would be relevant for surge motion, and pitch is dependent on both of them. So what we can do in the simplest way in order to understand the forces that come from an incident wave field is to say, and this is a little bit hypothetical, let's think about this wave field and how the local pressures at the geometrical description of the body change. So let's look at the geometry where the body is intended to be, but not consider the presence of the body in the water. So that's just an integration of the pressure at those surfaces without the influence of the surfaces. That's referred to as Froude-Krylov force. And it's just the most simple representation. The next level is to say, hey, this body is there, so there is a scattering happening of the wave, so there's a reaction or reflection of the wave. Let's consider that as well. These two terms, the incident wave field and the scattered wave field, are referred to as the diffraction wave field, or the diffracted wave field. And they compose together the excitation force that drives the system. I should mention that literature is a little bit not at odds with the definition. In some books, you'll find that the scattering is the superposition of the other two, but the principle is the same. Of course, this all holds in different degrees of freedom. Another sketch on the bottom right in relation to pitch excitations, where you see the distribution of the pressures. So all these forces are integrations of pressures over the relevant forces, over the relevant surfaces. And again, this is the force we were just talking about, the excitation force coming from the wave that will drive the system. Let's move on to an added mass. So what's the added mass? The added mass is a force that represents the inertia of the fluid that is being moved due to the oscillation of the body. It is a force that is in phase or a function of acceleration. That's why it neatly can be interpreted as an inertia, and that's a valid interpretation. It is the inertia of the water that needs to be moved while the body is moving, and It is frequency independent when the body is not in the vicinity of the free surface, but it becomes frequency dependent when the body is close to the surface. And now we're looking at, radiation is a consideration where you don't have an incident wave field, you just have flat water, and then you move the body in this water and you see what happens in terms of experience of forces. It can get quite tricky because this holds for all degrees of freedom. When you have complex shapes, 1 degree of freedom movement could create an added mass in another degree of freedom. So there are cross-coupling effects. And that, of course, gets even more complicated when you think of multiple bodies. On the right-hand side, you see a few exemplary terms. So let's look at this one. So this is a cylinder. This is all in 2D. And it's interesting to see that the added mass of this cylinder, when it's oscillating, is just the volume of the circle, or the area of the circle, multiplied by the depth, of course, if we think in extended 2D, and multiplied by the density of the water. So if the cylinder was the same density of the waters, you would have the inertia from the body itself and the same amount of inertia from the added mass. Back to the equation, this is what we're looking at. This is the added mass. So the mass term that adds to the mass of the body to make up the inertia in the dynamic system. Let's go to the next. Well, sorry for one more. This is just another description of more complex shapes, or an ellipse and what this looks like. What I didn't mention, if the ellipse is a circle, as you've seen first, so if A and B are the same size, in pitch, in a rotation, there is no inertia because nothing is being displaced. Okay, now we come to the hydrodynamic damping. So the damping is a force which is a function or in phase with the velocity. Forces like that, or terms like that, require energy to be transferred into the system or out of the system. So this is where we lose energy. How can I lose energy in this simplified fluid dynamic system when I do not consider, I should have mentioned that, viscous effects? So where can I lose energy when my body moves? I can lose it if I radiate waves. And this behavior is, like waves are frequency dependent, also the hydrodynamic damping, the radiation damping is frequency dependent. And it only occurs when I'm close to the surface, when I actually can radiate waves. It's zero when we're deep down in the water. Okay, and the same cross-coupling over the different degrees of freedom as well as different bodies occurs. On the right-hand side, we see multiple things. We see added mass, we see damping, and we also see a response amplitude operator here. And as you can expect, it's the typical shape of an oscillating 1 degree of freedom system. Reminding us on what we're talking about in the equation, this is the radiation damping. Okay, now we move on to wave energy as such. We've talked about energy flux. We talked about different wave shapes and energy content in the different frequencies, like we see on the right-hand side. We talked about realistic, actually measured spectra and simplified spectra in single peaks. It's a bit tricky because some real seas have bimodal spectra, which are badly represented with these regression functions on the right-hand side. We've learned that we can present the occurrence of sea states in a scatter diagram. There are different ways of expressing these. Heat maps are nice to see where the energy content is in which sea states. Directional information, of course, is also given in the resource. Resource maps are available for the US in a kind of simple comparison. The energy content or the power of the East Coast, sorry, the West Coast in the Pacific is equivalent to as if we had every 2 meters a live wire running at its full installed power. So it's just a simple idea to get a feeling for what have we coming in there all the time on annual average, of course. Can be much more at times. Right, let's move on. Energy conversion. So we talked about wave energy, and let's talk about energy conversion. We'll keep this very simple, but very instructive, I think, and very crucial and important to understand this. If I have a wave coming in to a wall, I have an incident wave field and I get a reflected wave. So there's the incident wave field, I get a reflected wave. When we superpose them, we get a standing wave. Nothing's happening anymore. There's no energy moving from anywhere to anywhere. So that's not what we want. On the right-hand side, we now release this wall on the right-hand side so that the incident wave exists, but also a radiated wave. We're moving with this, we're interacting with the waves. And if we manage to cancel the reflected wave with the radiated wave, then there's nothing going out visually, and there's only the original incident wave coming in to this machine here on the right, to this pedal, and everything's gone. So the wave energy is fully absorbed. So that leads us to the often quoted saying that a wave maker is also a good wave absorber, or the other way around. So that's an important principle. So we need to find a way on how we make this incident wave basically move into our machine and just magically disappear. And that is the evidence of that power is extracted, as long as we don't have other effects in there. Okay. That leads to requirements for the power conversion mechanism. So it has to do two things. It has to deliver the right interaction with the waves so that we achieve exactly what we just described. And that means that the wave energy is converted into a primary other shape, a form of energy, which is usually mechanical energy in the simple examples we have. The next step it needs to convert the secondary energy into the desired energy, which is typically electricity. Now, in order to do this, particularly the first point, the power takeoff mechanism has to do things. It has to provide a damping force. That's the energy extracting force, which is a force in phase with velocity, as we learned earlier. But it also has to get the phasing right of this oscillating force. That means, and that can be implemented by having restoring terms, so a term that's in phase with the displacement. And that, by its nature, is a short-term energy storing effect. So, and that's tricky. So we don't just always get power all the time. We also need to put some power in and get it back so that the balance is high. So these are the two things the PTO needs to do. Okay, and again, this in the equation, this is what we have on the right-hand side, the PTO force. Now, when we have all this and we have the numerical modeling capability behind, we can pick a site. We have the scatter diagram here slightly differently presented in a clustered way. And then we go to a power matrix and understand what kind of energy can be extracted in what seas. This is a very unusual example because it's for a very small device which operates over here. You've seen many other power matrices, and you will see more later on that are more for the larger devices. Okay. Now, and there they come. Here's an important benchmark study. I want to point towards it. Now, when we look at comparing technologies with their wave energy absorption capability, it's important to look at the annual average absorbed power. But this is not a relative quantity. It's an absolute quantity, which is, of course, you know, a bigger device gets more stuff out, I presume. But we want to have efficiency values. So we need to relate our benefit, the kilowatts, to some kind of a burden. There's a capture with ratio definition, which is the power that's being contained in the wave crest of 1 meter width. We had this at the very beginning as well in the previous webinar. We relate that to the power that the wave energy converter absorbs and related also to a characteristic length, which could be the width of the device. So that's this capture with ratio, is a good, clever quantity for wave energy. We can also relate the absorbed power to a characteristic mass, to a characteristic surface, which is maybe an identification of constructed surface that needs to be done, or the intensity in which the PTO needs to work, so force of the PTO. And all these quantities have been identified in simulations for 8 different systems. And I just want to show you this. So there's a description of the system, a sketch. We have some dimensions. We have the resulting power matrix. And we have the results of the quantities just described for different sea states. So this is Ireland, Lisbon, European Wave Energy Center, and the France site. And let's just flick through them to see the different technologies. So the key technologies have been investigated like that. And the only thing I'd like you to look at is the power matrix, which is very different for the different technologies. Here are 3 other ones and 3 more. So you can look up this piece of work. It's really a good benchmark piece of work, which was done about 10 years ago. Is that right? Yeah, 12, 13, 12. That's what it is. Okay. Let's move on. No, we don't move on. So this is the result of the benchmark study of 2 of those 4 quantities that we're talking about. So this is absorbed energy over mass and absorbed energy over surface. Something that sticks out here is performing quite well. Is the bottom fixed oscillating flap. The bottom fixed area of Heath systems is also not performing too badly. So you can see a comparison here. And so given the wide variety of technologies that we have, it's really crucial that we find ways on how to compare this. And I want to point out, this is only one aspect. This is only a very simplistic, by the modeling as well as by the quantities used, expression of the wave energy absorption capability. This is way, way far away from the techno-economic performance of a real device. Technologies, we looked at categorization of technologies by location, by orientation, by mechanism of extraction, by reference, reactional reference, as well as by degree of freedom. So this, again, in white, in heading, this is from the previous webinar. We looked at a few concepts and how they move. Let's just give you reminders of these in the animations. Here an oscillating water column, an overtopping device. Okay, and the PTO, very different ways of implementing the power conversion, the internal power conversion. So let's look at a few simple methods. Well, not simple, but a few methods. Let's look at them in a simple way of technology development. Of course, there's a wide variety of simulation tools. I can't go into them. It's a whole world by itself. Since we had these simple equations earlier, I just mentioned them on the right-hand side. When we solve the fluid dynamics in the most simple way, in a linear way, we can feed frequency domain solvers, time domain solvers, and stochastic models with that. And it can get much more complicated and much more high fidelity, but we have to skip all that. So in terms of tank testing, a bit more visual, some examples here for what you do in the tank. You do some fundamental concept understanding with very simple and small scale devices in cheap tanks. Here is this is WaveBob. I used to work for this company. This is a 1 to 75th scale model, and the PTO in there is only a friction damper. Then you can go to larger scales. That was 17 scale, wave energy absorption, code validation, pretty precise and well measurable, and much more sophisticated. That was in Maren in the Netherlands, excellent facility, where we had a linear generation power takeoff mechanism, which is very precisely controllable on many different control schemes. So that was done there. And we also had a small model to be small in relation to the waves that can be produced in the basin so that we can test survival. So that's the kind of typical thing you can do in a wave basin. And here, just one example of core power of a bench test. To my knowledge, the largest installed capacity of a bench test goes up to peaks of 7 megawatts. So there's a linear test arrangement where the linear motion in the power takeoff and everything that comes with it that is then later on used in the sea is being tested in the bench. And I cannot emphasize more how critical it is to test such equipment on land before you put it in the sea. I think it's a no-brainer. You don't want to have fixed anything at sea if you don't have to. Okay. At sea, there are test sites. We have some test sites in the US. The main ones are the one in Hawaii, which has been in operation for a long time under the Navy, and we have one under development, PacWave, at Pac Pacific. In Europe, we've got quite a bunch of test sites. The most important one to mention is the European Marine Energy Center. Many of the well-known devices have gone through tests there, and they're also partners to support us in developing the US site. Let's go to history. We have early developments. What happened pretty early in 1799, we've got the first patent by a gentleman called Girard, a French person, and remarkable, so very early. I don't even know when people started writing patents, so that's interesting for me to know as well. So we have thousands of patents in the meantime. Something close to home, in 1898, I presume maybe Mrs. Wright, developed a floater that's connected to a mechanical system which drives a hydraulic ram. And on the right-hand side, we have a patent from 1920. And you can see here there's the water surface. There's a duct to an internal free water surface that moves up and down, pushes air through a ducting system through a turbine. So this is the first oscillating water column reflected in a patent. Other early developments are, and which is very remarkable, the first commercial application of wave energy was implemented by, later on called Commander Masuda, who developed a wide variety of oscillating water columns, and the one I'm referring to here was used as a navigation buoy, and large numbers of those have been installed and used in Japan, but also later in the US. This is what it looks like. So this is the buoy you can imagine with the mooring. What's happening internally, you have an internal water surface moving up and down, pushing air through a one-directional turbine, and with a valve system to ensure that the air goes this way and another way back. Oscillating water column in operation commercially, nice. There are lots more oscillating water columns around the place. This was an early test center in Pico in the Azores, so in the middle of the ocean. Here's what it looks like. Again, an oscillating water column is mentioned, sketch on the right, on the left, and the actual design drawings on the right. This device is not in operation anymore. Pico has great waves, but not such a good supply chain in terms of labor skills as well as material and other things. Okay, more oscillating water columns. Oscillating water columns are probably, thank you, Samantha, are probably the most developed, the most investigated wave energy converter archetype. Here's a Scottish device. Here's the turbine internally, quite sizable, maybe larger than you might have expected. There is a device in Australia, 2005. We have a Norwegian technology in the 80s. We have another Scottish test site, which was very, provided a lot of learning. And we've also had a lot of activity in India. Then we can go to floating oscillating water columns. In Japan, we've had the mighty whale, 50 meters long, floating oscillating water column. There's more floating devices. A large test bed has been used, a kind of a converted ship with several oscillating water columns. All of these boxes that you see are air chambers. That has been a test bed for oscillating water columns. Another Australian device with several chambers, and an Irish technology, which is now in larger scale, built also in the US and ready to be tested in the Navy test site, OE buoy, which is a backward bend duct buoy. The interesting thing about floating oscillating water columns is that the internal water column moves. That's critical to push the air, but the body itself moves as well in multiple degrees of freedom. So it's important to put these dynamics nicely together to get the maximum internal displacement. Turbines are needed, particularly for oscillating water columns. Bidirectional turbines have been developed. That means they can accept flow from both directions while maintaining the same rotational direction. Clever stuff. And here's some designs. Here's the Wells turbine, which has a pitch control. This design that you're looking here has an installed capacity of 400 kilowatts. So quite serious as a prototype. Then there are other technologies which use concentration of flow and increase of angular impulse. Then there's other technologies where there's symmetry, where leading edge and trailing edge are being swapped in the rotational directions. So there's lots of different design. There's whole other classes of turbines as well. One important technology is the Salter duct on Edinburgh, named after Professor Salter. This is the duct that came out of different considerations. And here is a very historical important picture, because this is the duct in operation. So it's a pitching device with this shape that you see on the left. And we can see waves on the right-hand side, and we can receive wonderful stillness on the left-hand side, which is exactly what we want to see, that the reflection and the radiation of the body creates exactly that situation that nothing is lost and nothing goes, nothing is left and everything is absorbed. This device has also been tested in survival. So here you see an extreme wave, 100-year wave, and here's a time series on the right-hand side of the survival situation. But you can see at the bottom, this system doesn't have an end stop, which is very handy. It's one of the critical problems to be avoided in wave energy, because it can fully rotate if the wave and the wave forces required us to keep the forces under the acceptable levels. The duck has been developed in laboratory extensively. These are all individual elements. So far, we looked at a 2D. Now we have 3D. So you make this thing a terminator device, which is very wide. And that's what it looked like in the basin. Very impressive, large number. And you can imagine a long structure like this needs to be compliant in some way. So the individual elements are also, with respect to their relative angular displacement, able to extract power. And this, you remember, this was all done in analog times. So I would say quite an achievement of sophisticated laboratory type equipment. The salted duck was never really built at the scales that was intended for. It was suffering from kind of the end of one era in the 80s of wave energy, when the nuclear industry came in big strong in the UK. Here is a device that has used the salted duck to be equipped over shape adjustable and width adjustable structures, vectors. And here is a prototype in operation. So you can see these individual salted ducks moving. A clever arrangement is also to make them hollow, not to have the need for all this ballast to deal with the buoyancy. Another consequence that came out of the salted duck is the device Pelamis, as you've seen before. So it's an attenuator. So the design configuration here, model of the Pelamis, was opposite to the normal design consideration. So when you think of a wave energy converter, you think, hey, what can I do to absorb waves really well? And after that, you think, hey, you know what I need to do to make this thing survive. But you can go the opposite way. You can say, I'll choose a configuration. I'll go to the next slide. To choose a configuration that's really good at surviving extreme waves. And one example is to dive through waves. You see a surfer diving through a wave, and this is exactly the same principle that's implemented in Pelamis. So you can dive through a large wave, so you're transparent to the destructive waves. Beautiful. And so you can see in a sketch here at the bottom as well, where you see the larger the waves are, the more the device dives. This has been simulated in very high fidelity simulation environments, and it's been validated in a tank. So that's pretty beautiful. Then the question is, how can I make sure that the energy absorption is large? Here are just a few pictures of embodiments. These devices were built. You see them on the bottom left. Quite serious demonstrations. An array of 3 devices was deployed, and also serious bench testing. Now let's go to the challenges. I want to remind again of what we discussed previously. So these developments are expensive. They are risky. Things can go wrong. Let's see. They are slow. Even if we do a good job, it can take some time. And they can be rigid if we're confined to a narrow IP space, which unfortunately is a bit of a sickness that some startups are suffering from or addicted to. Okay. So I want to make one thing. I want to emphasize one aspect in terms of challenge. We will not come so much to the solutions. I'll just give pointers towards these. So one important thing is, how do you compare the technology development and its characteristics of wave energy to others? And I want to use 2 terms, technological evolution and intelligent design. Intelligent design is kind of deliberately a little bit of a provocative term, and we'll come to this in a second. I allocate these terms to the 2 domains of wind energy and wave energy. Let's talk about wind energy first. With technological evolution, I mean incremental improvement of a technology in different operational conditions. And so what were the conditions for wave energy? First of all, there was a much earlier convergence of concepts. Clearly, there were many different concepts, different orientation of axis, lift and drag devices, and other devices too. But the kind of the sorting out what's best was relatively clear. And there was a relatively strong, not 100%, but a strong convergence towards the horizontal axis with 2-3 blades on it. Then what's also important, we've got a technical feasibility and industrial production and market applications and opportunities at all scales. You know, I'm sure you've seen little battery chargers up to farm size individual off-grid applications, up to what we now have. I think the largest offshore wind turbine prototype has 16 megawatts and something around 250 meters rotor diameter. So, and all sizes were possible and all of them had applications. So an incremental increase was well possible and has happened. The next very important thing is that there were skills available from other domains, from aviation in terms of production and so on at high sophisticated level. The prices that these industries require were not transferable to renewable energy, but the skills were there, are there. Another very important aspect is that these applications and markets allowed initially easy access, which meant they allowed relatively high failure rates. So in Denmark, the farmer might have just got used to that every Friday he has to fix the turbine or exchange a part or whatever. You know, I'm just saying that is in a joking way, but it was possible to run these systems at all levels of failure rates and reliability. Now, all of this is very different on wave energy. First of all, we have a large spectrum of different wave energy converter concepts. What we've shown you today is just a small, well, it's a subset of a wide variety of technologies, and we still haven't converged. There's a strongly decreased opportunity for markets at reduced scale. Of course, we have all the ambitions and all the very important applications in powering the blue economy. However, the tricky thing is that those device designs that work as small devices in the large Cs that we have, they are not upscalable to work in the large Cs. Other devices may be required for that, because we have in the system dynamics, often, not with all devices, a coupling either to the frequency range of waves, long and slow, long periods, slow, or to the dynamics expressed by the size, long periods. So the typical device tends to be large, tricky to do something at small scale. Then we have a limited transferability of skills. We might think of offshore oil and gas and shipping industry, correct. However, those industries have no fear of capital expenditure. If it doesn't work, make it thicker, make it stronger, beef it up, you know, particularly oil and gas. The other thing is typically these are single bodies, ships, oil rigs, mooring, of course, but, you know, they would try and avoid to have two bodies very close to each other that can move relatively to each other. Nobody wants to see this. We have to do that. Another important one, when you go to sea, now this is about failure modes and reliability, things have to work right away. In an extreme sense, if your prototype has a failure, even of a component, the beginning of winter, you can't access it, you might lose the entire winter, which might have 80% of the annual average of the annual energy content. So reliability has to be high right from the beginning. So that's why I would refer to this not as technological evolution, but as intelligent design is required right from the bat. Okay, in terms of other learnings and leads for solutions, I think in overall, I won't read out these individually, we have much better methods on how to deal with the technology development, because methodologically failures have been made as well. And since this is a very tricky domain, scientifically as well as from an engineering perspective, methodologies have to be right. Of course, and also manufacturing and materials, things have moved on a lot. And we are looking at paradigm shifts. And back to the topic here, of course, we want to have the shift from solid body systems with concentrated power takeoff to the potentially deformable, but most importantly, distributed embedded energy conversions. And hopefully you will help us to crack that nut here. And here I'm open to questions. Thank you very much. So I haven't looked at the chat yet. If anybody wants to moderate that, that would be helpful.
Yeah, we had a question come in about participation in the webinar for the leaderboard. So I just wanted to call that out, that teams must complete the initial eligibility confirmation on HeroX. And then once you attend, we compare the attendee report to those folks that are registered. So no additional step is needed there to get your points.
Okay, open to any questions. I think we can open the mic, can we? Or we'll use the chat. We have time for questions.
Yeah, we'll be using the chat. I do see another quick question about the eligibility. So eligibility from phase 1 does not carry over. You do need to go back in there and reconfirm.
Maybe one important thing for phase 2 is you do not have to have been participant of phase 1. So it's still open for everybody. You're not too late. Any technical questions, anything that was too fast and that you'd like me to go back to?
And also, I think, Joachim, earlier you had suggested if folks have suggestions for any areas that they'd like us to dive deeper into in these webinars, especially as we go into phase 3, we can go even deeper into any of these topics. So if there's something you'd like us to go
Yeah, thanks
in
for
more depth.
Yeah. So in this opening, this offer holds for the 3rd version of the Wave Energy introductory webinar. So which will be another extension of this one. And it holds also for all the other themes, which are TPL assessment, DEC tech, technology in general, distributed embedded energy technology, as well as innovation methods. And of all of those 3, you will have a phase 2 webinar and you will have a phase 3 webinar. So we can customize this to your needs if you express those.
Barry, you had a question?
Go ahead.
Yes,
Yeah.
yes, actually. Hi. Thank you. I was wondering about the 2-body experiments, where they're going.
Sorry, which one? Which 2-body experiments?
You mentioned 2-body experiments and the dangers that are involved in doing that, but the high potency as well.
Okay, yeah. So what I'm referring to, let's say when we just take this example here, we have here 4 bodies. They are hinged and have angular relative motion in heave and in pitch. And this is, hydrodynamically and survivability and everything more challenging than dealing with a ship. That's what I was pointing out towards. Or even with an anchored ship, because this device is also moored. So so those skills, of course, we have experience with ships, or oil and gas, forget now the right terms, but offloading platforms. So there needs to be docking, there needs to be getting close to, but this type of system is not typical, at least for the normal oil and gas or shipping industry.
Okay, thank you.
Sure.
Looks like we have a question from John Newport.
Exhaustive presentation. Well, I hope you were able to survive it.
John, you should be able to unmute yourself if you want to ask your question.
Yeah, maybe I, as far as I understand this question, and Blake and me can respond to this. So the DECTEC prize, we are not requesting anybody to invent a wave energy converter, nor to customize their DECTEC deck aspect, or the DECTEC metamaterial aspect to a wave energy converter of any type. So we've specified in the rules some high-level ranges of quantities of motion dynamics and energy densities that in which you can work in. So you're even freer, I would say, than what you're considering here. You have the opportunity to say, okay, I don't like these ranges. My novel different wave energy converter I'm envisaging, and which I will want to put in my DECTEC metamaterials, is operating differently. Then you can show us that and we can think about it. That's fine too. But yeah, basically you can choose them within those ranges. Maybe Blake, do you want to add to this?
Yeah, I think what the message I would give to the contestants regarding the presentation, the wonderful presentation that you just put together, Joachim, is this gives context, this gives background, especially in terms of DOE's Water Power Technology Office efforts in the domain of ocean wave energy conversion. It has more to do with that than I think it does with the actual phases of the prize, because to Joachim's point, no one in terms of a contestant is being required to develop a wave energy converter. So today's webinar is giving background into the domain of wave energy, but for the prize, we're looking at like a subset of technologies, the collection of individual distributed embedded energy converters together and an individual energy converter, but not a full-fledged WEC. So to come full circle, I think for my own personal perspective, the best way to think of this presentation is that this is the domain that DECTEC's being utilized within, but the prize itself is being limited to not have to take into account the design of an actual wave energy converter. You could even think of this presentation as a historical context with what we're working with.
Thanks, Blake. Yeah, Paul, and now I see that it's from you. Hi, Paul, and thanks for the comment about the presentation. Does that answer your question, roughly? Okay, we presume it does. If not, what is the comparison criteria between different designs? Good question. Well, there is possibly, so the thing is, how do we assess these different contestants or teams in the prize? Very valid and important question. So what we're trying to do is that we do not bring it down to very simple single metrics, like, for example, in the benchmark study of the simulations. We try and assess more holistically how promising the individual proposals and demonstrations of the teams are. And for that, we are using a simplified technology performance level assessment. So it's intended to be more holistic. It's not precise in the individual quantities that are in this range of aspects, but it is precise, let's say, in the sense that it tries to consider many aspects. So it'll be a guided multi-criteria assessment process supported by TPL, a simplified TPL method. And we have dedicated webinars for that.
Yes, and I also wanted to point out that the scoring criteria is in the official rules document, so that those statements that you address in your submission materials, as well as what is required for this phase, is all covered in that rules document.
Great, thank you. And thank you, Paul, for the questions and the interaction here. It's very valuable for everybody.
So Yakima, a question came in the Q&A. I'm not sure if you see that there, but it says you mentioned Lisbon testing. Is that information available? And have you ever heard of a OWC turbine using anything other than a Wells turbine and or a modification as in guide vanes?
Yes, okay, we have. Thanks for the question, Steve. Yeah, we have several other designs, and I want to go back to it. So the most prominent one is the impulse turbine. And I don't have an image of it, but let's go to the turbines. Maybe I can explain it without an image. Here we are with the turbines. So the Wells turbine, you see up here, and here it is guide vanes. Another arrangement with guide vanes is when you replace this Wells turbine and you have much more curved guide vanes and also very curved blades on the rotor, so that you could say that the force application on the rotor primarily comes through momentum directional change. So the guide vanes lead the flow into the plane of the rotor, and the rotor is shaped that the flow is let's just say turned about 180 degrees and goes out by guide vanes again. So the impulse change due to directional change is the transfer mechanism. So it's quite different to the lift turbine here. So the turbine in here is typically an impulse turbine, and this one is also very different. So let's think of the Wells turbine here with pitch control. So you can imagine that this blade, always rotating, this side downwards, will have pitch angles going to one direction for one directional flow, and the pitch angle going to the other direction to the other directional flow, and maintaining always the leading edge is always the leading edge. Another opportunity here is this Dennis Alt turbine, which was developed or used in Ocean Links in Australia. And here you see maybe that the blades are symmetric with respect to this axis. So the leading edge and the trailing edge are identical, but they're not symmetric in terms of their curvature. The Wells turbine was symmetric in terms of their curvature, so the symmetries are swapped out. So what's happening here is that the curvature or the orientation of the blade is such that the curvature is always in the desired way. However, for that, you have to swap the blade trailing and the leading edge. That's why the symmetry is in the other direction. I hope that was relatively clear. So yeah, these are three quite different designs. There are also not axial but radial turbine designs. Yeah, that's a minority. That's all that comes to mind. I'm sure in 10 minutes I can think of another one that I'm forgetting now. Does that help?
Yeah, I think it helps. Joachim, we have a couple questions in chat regarding electroactive polymers and the status of the development of those WECs associated with electroactive polymers.
Okay, maybe we'll do a dual one on that as well. I will only say that this technology, Pelamis, SBM, single buoy mooring, which is an offshore engineering company. Let's go right to the back. That's developing this concept on the right. I haven't been in touch with SBM for quite some time. My understanding is they are still developing. The next goal was to have a maybe quarter scale demonstration in the Mediterranean Sea. They have sophisticated laboratories to develop their electroactive polymers in a roll-to-roll manner, so in a manufacturing way that could scale up to what's needed and also to maybe cost that's needed. But in terms of performance and how close this is to being practical, I can't comment. I've been, need to catch up with them again. But in terms of the principal capabilities of electroactive polymers, maybe Blake can add something.
Yes, thank you, Joachim. So I'll just second everything that Joachim said there. We have a company, SBM Offshore, looking to develop they're calling it an S3 device. It uses electroactive polymers, and ostensibly electroactive polymers, especially for their design, is based on dielectric elastomer generators, so this notion of variable capacitance. Last I heard, they're still in they're aiming for a 1/4 deployment somewhere in the Mediterranean. And also to Joachim's point, they're using roller processes. So think paper companies where they basically extrude paper and not paper, sorry, a polymer, the dielectric between two electrodes. The dielectric's an elastomer, it stretches, that's the power takeoff. And I'm looking at the chat right here. It's the question is it still in the conceptual stage? I would say it's probably both simultaneously the most conceptually type of wave energy converter, especially if they're moving to 1/4 scale. But on the other hand, it's probably one of the most well-developed technologies within the domain of distributed embedded energy converter technologies. So from the historical context, pretty new idea. In the context of deck tech, probably one of the most well-developed.
Thanks, Gary. See you next time. And just a quick comment back to the question about Lisbon and the turbines. I'm trying to credit everybody here. Says a substantial amount of research and design has been done in Lisbon at IST, Institut Superior. No, I can't express it. IST. And Wells, of course, is from the UK. And Edinburgh has done a lot of work on the pitch regulated Wells turbines. And yeah, we have also work in Australia and also work on a lot of work in the early oscillating water columns in Japan. So it's a lot of good work that happened. I think oscillating water columns are a very good example to, it's a very obvious solution when you see it, but it's non-intuitive. It does very many things. It's an internal gearbox by having a large body of mass that's moving slowly, converted to a finite, to same volume, but to a very fast flow in a narrow duct. So there's a kind of a fluid dynamic gearbox, you could say. And you're operating outside of the water. So, you could call this a paradigm shift in how to do wave energy at the time. So what you're up to here in deck tech in InDEEP is not the first time we've had a paradigm shift. So be encouraged that it's possible. Okay, I think we're coming to the end of the time, right?
We are. I do see that Barry has had his hand up for a little bit here, and I wanted to give him an opportunity to ask a question before we head out.
Yeah, hi. So Joachim, you said that something about we don't have to come up with a complete system, just part of it. Can you elaborate on just real quick?
Yeah, so we've talked about power takeoffs here, which are subsystems to the wave energy converter, like a hydraulic system that you see on the bottom left. And the analogy to that in the deck tech world are the decks, so the transducers that, for example, change deformation or work with the deformation, mechanical power input to electrical power output, and how you glue and put these together, which we call deck tech metamaterial. But we don't, so if you come up with this deck tech PDO and show us what you have in mind, and then you're fully in the scope of this competition. You don't even need to consider that it goes into a Pelamis or into a bottom hinge flap or into something else. That's why you do not need to come up with a whole system. You just need to show us your solution on how the distributed embedded energy conversion world power takeoff mechanism could look like. Does that make it clear?
I think so. I think it's better. Okay. Thank you very much.
Sure. Okay, then maybe just a big thank you from me that you took the time, and great to have all these questions and interactions. Much appreciated. See you
So-
in the next one.
Joachim, real quick, is there a place where we can find maybe ideas about what kinds of I guess challenges are posed by these things that are already in the ocean that need something better? I guess I'm trying to figure out how I can find what the challenges are currently.
Well, the challenges are, so the things that are out there that you could put your deck tech material in don't exist. One example, one exception is what you see on the right-hand side, the SPM system. So what we want to do with the prize is that we want to compete over and innovate new internal power takeoff mechanisms, the formation of distributed embedded energy converters, so that we then, as this enabling subsystem, can start innovating wave energy converters that suit the subsystem.
Perfect. Perfect. That works. Thank you very much.
Okay, cool. Yeah. And there's one more, Steve. I just read your comment. Well, you're mentioning that the Wells turbines have spaces between the blades, and that is associated with losses. That's not really correct. You know, look at wind turbines. They hardly cover the rotation, so the swept area. I mean, they rotate over the swept area, but they're completely open, and that doesn't mean that there's losses. It's just a high velocity, low solidity turbine, or turbine. Guide vanes and complexity from guide vanes add complexity, sure, and even there are even adjustable guide vanes. You know, you have the guide vanes themselves, of course, would ideally look different in the different flow directions. Like you have pitch control, you would like to control guide vanes, and there are passively controlled guide vanes as well, which flap open and close or have two end stop situations. So, and that of course gets complex manufacturing and reliability. We developed a bidirectional impeller design. Interesting, show us. Have you heard of any work in this area using bidirectional impeller? As the definition, what an impeller is, so an impeller, I presume, is what you refer to as a ducted turbine, which has high solidity, if that's correct. What maybe what goes a little bit in direction is multi-rotor devices and counter-rotating turbines. They're all ducted, so in terms of impeller. And yeah, I think we could have a discussion about using all the energy. You know, you can have in terms of turbo machine, you have kind of displacement machines, and you've got turbo machines in terms of lift-driven machines. That the one doesn't have leakage over the other doesn't necessarily mean that it's better in terms of capturing all the energy. A scroll style impeller. Okay. Yeah, I'd love you to get in touch and show your design, and we can have a chat about it.
Just wanted to add a quick thing as we wrap up. So we have 4 more webinars planned in the next 4 weeks. So please go to the HeroX website to register for those. And also the prize team is very much desiring to support our competitors and participants to the greatest extent possible, particularly those who are coming in from outside of wave energy. And so we are doing the absolute best that we can to provide y'all the context and resources and background information that would be helpful. So if y'all have any ideas for other content that would be helpful, or any other questions that arise, or something that we didn't cover because we can't think of everything that y'all might need, please feel free to put it in the chat, to reach out to us. We are very welcoming and receptive to feedback, and we'll have additional webinars based on the suggested content that y'all say that y'all need. Thank you.
Great, thanks, Nicole. You'll find us with our emails. So mine is in here, but if you Google our name and NREL, you should get us, all of us.
Perfect. Thank you.
Sure. All right. Thank you very much. See you next time.